This is first time I'm lecturing in CLT. To make me feel free, you have to maintain a little bit silence. Now, it is about analog circuits. Analog circuits, the subject is considered to be the core. In fact, it is the corest of the core as far as communication engineers are concerned. Because the topics you study under the title analog circuits, those topics all are highly essential in the design of transmitters, receivers that goes into the making of a electrical communication system. If you look at a transmitter circuit, there you can find plenty of amplifiers and also oscillators. In fact, most of the transmitter circuit or most of the receiver circuit, almost 90% of the that big circuit consists of several amplifiers and some oscillators. In earlier days, this subject analog circuits used to be called analog electronic circuits. Maybe because of shortening the length or to have a short title, nowadays it is being called analog circuits. The title itself, most of the times, title itself carries, it gives some information, good amount of information regarding the contents of the subject. Circuit, you all know, is a combination, an interconnection of various electrical elements like R, L, C, and source. Electronic circuit is a circuit where you can find one or more electronic components like diodes, transistors, etc. So electronic circuits, analog electronic circuits. Name indicates that circuits which deal with electronic circuits which deal with analog signals. In brief, analog circuits, it deals with amplifiers, only amplifiers, nothing else. Different types of amplifiers. Some of you may get a doubt that oscillators are also there. So oscillators are also amplifiers. They are feedback amplifiers obeying certain condition, unity, loop gain condition. So all amplifiers, that is analog circuit. With this brief introduction to the subject, let us go a little bit specific contents of the subject. Several types of amplifiers are there. Amplifiers is not a single circuit like diode. Diode is a family name. Transistor is a family name. In each of these two families, several types are there. In the same way, amplifier can be thought as a family name. Several types of amplifiers are there. Most important types are included in the syllabus. Higher level of amplifiers you may be studying later. For example, parametric amplifier are there. They require some higher level knowledge, so they are placed somewhere in fourth year or second semester of third year. So here, basic amplifier types are included in this subject. To begin with, single stage amplifiers. You all know amplifiers are nowadays they are semiconductor circuits. They use semiconductor devices, transistors, as active elements in the design of amplifiers. If you use a single transistor, single active element in the design of the amplifier, then that is single stage amplifier. Two types are there. One is BJT based, BJT single stage amplifier. Another is FET based. FET-based single stage amplifiers. In BJT, three configurations are there. By this time, you must be knowing what is CE, what is CB, and what is CC. As far as FET-based amplifiers also, single stage, there are three configurations. What are they? CS stands for common source configuration, CD common drain configuration, and third one is common gate configuration. BJT similarly CE common emitter configuration, common collector configuration, common base configuration. Those who are fully aware of configuration, no problem. For those who don't have an idea, I want to tell what is CE. Transistor is basically three terminal device, and we need two terminals to give input and two terminals to extract output from the transistor circuit. Okay, so one terminal becomes common for inputting two terminals, for taking output to two terminals. Actually, four terminals are required, but a transistor is a three-terminal device. So one terminal must necessarily become common for input and output. If emitter is common, then there is common emitter configuration. If base is common, then that is common base configuration. Similarly, CC. In case of FET also, if the source happens to be common to input and output, then that configuration, that amplifier is called CS. If a gate is common gate, and the third one is common drain. Before going further, I want to tell one more point. BJT and FET, MOSFET, their appearance-wise, they may be different, but if you go a little bit deep into their functioning, you can find a lot of similarities. In fact, if you study, then you can find that FET and BJT, they are not at all different. Inside, their operation is almost same. Only outwardly you can find some difference. Appearance-wise, they are different, but as far as inner physics is concerned, they are quite the same. This sameness, inner the sameness of the physics or functioning of the devices, they appear outwardly also. Emitter terminal behavior is, you can find a lot of similarity with the behavior of source in case of FETs. And the base is its behavior, its functioning is similar to the functioning or purpose of gate in FETs. Similarly, drain and collector, they also, you can find their functioning somewhat, their working somewhat similar. From that, we can infer, not only infer, we can observe BJT in the CE configuration. Its properties, its characteristics, its functioning is almost the same as FET in CS configuration. CB's functioning characteristics, properties, they are similar to CG. In fact, you all must be knowing base is used for controlling the flow of current between emitter and collector, base control. Similarly, gate is used to control the flow of current between source and drain. Purpose of base is to control the flow. Purpose of gate is to control the flow. Names are different, but their purpose is same. Similarly, CC configuration, its behavior is, you can find characteristics, DC characteristics and all that. They are very much similar to CD. CC, CD goes well. Now, after having some idea regarding CA, CB, CC, CS, CG, CD, one or two points I want to tell you. CA offers you all best performance. It is considered to be the most versatile. CA's voltage gain is very high, current gain also very good, high input impedance, high output impedance, all good properties. Same is the case with the CS. CS properties, its performance is very good when compared to CG and CD. One thing I want to tell is about amplifiers, not only amplifiers, about in electrical devices, impedances, their impedance characteristics, input impedance, output impedance. These two are important characteristics because they decide the way this particular device interacts with the rest of the circuit. For example, there is a device or amplifier, take amplifier. There is an amplifier, its input impedance is low. Then what happens? If you connect a source to that amplifier, the amplifier circuit starts drawing more and more current from the source. When you draw more current from the source, what happens? The performance of the source starts deteriorating. Its lifetime starts decreasing. This particular negative impact on the source is called a loading effect. In the same way, when the output impedance of the amplifier is small, this amplifier starts loading the next stage of the amplifier. So, in impedances of circuits, devices, in particular amplifiers also, they are quite important aspects, specifications pertaining to the circuits. Of course, amplifiers, you all know, amplifier is there to provide amplification. What is amplification? Amplification means making a small signal into a large signal. If the voltage of the signal is made large, then that is voltage amplifier. If current of the signal is made large, then it is current amplifier. If it is the power of the signal that is increased by the circuit, then that amplifier is called power amplifiers. We have voltage amplifiers, we have current amplifiers, we have power amplifiers. Several different types of amplifiers are there. As I already told you, C offers best performance among CV and CC BJT amplifiers, and CS offers best performance among the three types of FET amplifiers. In brief, C, as I already told you, it offers a good amount of voltage gain, current gain, high input impedance, high output impedance. So you can use it as a voltage amplifier, you can use it as a current amplifier. If you want, you can use it as power amplifier too. All good, but see, I need to tell you, it offers everything good. Performance is very good. Of course, it has one serious drawback. That drawback is a result of Miller's capacitance. You might have studied Miller theorem. According to Miller's theorem, the feedback capacitance gets multiplied and appears across the input terminals of the amplifier. So this multiplied capacitance reduces the maximum frequency at which the amplifier can be operated. The net result is you cannot use the amplifier at high frequencies. So the limitation, the frequency limitation is set because of Miller's capacitance. This Miller's capacitance is the specialty of C. So remember this much, C is all good, everything is fine except these two aspects. One is limitation on high frequency operation, and the second thing is when there is high frequency limitation, it results in reduced bandwidth. Reduction in bandwidth means system becomes slow. high bandwidth, low bandwidth. High bandwidth means fast, acting fast. Low bandwidth means slow. So CE is everything fine except this drawback. Similarly, CS. CS offers, it's very good, it's also good amplifier. High voltage gain, high input impedance, etc. etc. High output impedance, relatively high input impedance. Everything is fine. This CS also suffers with the same drawback, that is Miller's capacitance, and as a consequence, reduction in high frequency operation. You cannot operate it beyond certain frequency. That limitation is there. Regarding CBCC, CB is voltage amplifier. Its current gain is nearly unity less than unity. It acts as uh, it has applications. In fact, CB application is at high frequencies. CB doesn't suffer. CB, CC, CG, CD, they don't suffer with Miller's capacitance problem. Only CE, CS suffer. So hence CB is widely used. CC also you can use, CG, CD, you can use at high frequencies. When it comes to practicality, CB is used widely at high frequencies. In fact, to design amplifiers that work on board the satellites, their CB is used, CG is used. Okay, CC, when it comes to CC, it is a current amplifier. It has a high input impedance, low output impedance, and you can CG, CD, their properties correspond to CB, CC, there is nothing much to do. So this is as far as a single stage amplifiers are concerned. So before going further, two versions are there as far as single stage amplifiers are concerned. One version employs BJT, another version employs FET. When BJT is employed in the design of single stage amplifiers, there are three configurations: CE, CB, CC. When FET is employed, three configurations: CS, CG, CD. CE and CS are most versatile. This much information you must have in your mind. Now, single stage amplifiers sometimes they are unable to meet the requirements. Let us suppose I want a gain of 100. My requirement is there is an application and that application requires a gain of 100. But a single stage amplifier is able to give only, let us say, 25. Then how to get 100? One way is going for a two-stage amplifier. Each stage may be providing 15, 15, 15 into 15, it is more than 100. In that way, we have an amplifier which satisfies the requirements of our application. So we go for multi-stage amplifiers when the requirements of the application on hand they are not met by single stage. These requirements may be in terms of gain. Most of the times it is gain. Sometimes it is requirement is in terms of input impedance. Sometimes it is in terms of output impedance. Sometimes it is in terms of frequency of operation. I want to enhance the frequency of operation. Suppose there is an amplifier, it is working at low frequencies, or it can work only at low frequencies. I want it to work at high frequencies. What to do? So some modification I have to do. Something I have to do. That something is adding another stage and make it as an integrated two-stage amplifier. So that way we get these two-stage amplifiers. Two-stage amplifiers are most important are mentioned there. Darlington pair is an important two-stage amplifier. Cascode pair All of you note it is not a cascade. Cascade is different from cascode. O, A. Here O is there, there it is A. Cascode pair and differential pair. These three are two-stage amplifiers. Other types are also there, two-stage amplifiers, but these are considered most important. First, what is Darlington pair? Darlington is the name of a gentleman. He designed this particular amplifier circuit. So to remember his contribution, this particular pair is called, this particular amplifier is called Darlington pair. What is it? If you go into the circuit of Darlington pair, you can find two CC stages. CC stage, output of one CC stage connected to another CC. One more thing I want to tell you before going further. Analog amplifiers. We are studying analog amplifiers in this particular subject. All types of amplifiers, single stage, two stage, tuned amplifiers, power amplifiers, feedback amplifiers, oscillators, all these circuits, they have two versions, BJT version, FET version, except one amplifier. That amplifier is Darlington pair. Darlington pair or Darlington amplifier, two-stage amplifier, it doesn't have FET version, only BJT version. Why it doesn't have FET version? Reason is Darlington pair has come into being to enhance the input impedance of BJT amplifiers. BJT amplifiers, they suffer with one drawback in general. The general problem with the BJT amplifiers, any version amplifiers is that their input impedance is low. CC is considered to be the one which gives maximum amount of input impedance. Even that input impedance is also considered to be low because they found that even CC is loading the sources. When source is loaded, as already mentioned, the life of source comes down, the performance of the source comes down. So loading of the source is a serious problem as far as BJT amplifiers are concerned. To avoid this problem, what requires to be done is we have to somehow increase their input impedance. How to increase the input impedance? On this problem, Darlington worked while he was working in Bell Laboratories, and he came out with a solution. That solution is if you add another CC stage to a CC amplifier, CC, it results in a pair, CC pair, and this CC pair is able to give enhanced input impedance, thereby reducing the loading effect on the sources. So basically CC Darlington pair has come into being to enhance the input impedance of BJTs. But when it comes to FET amplifiers, you can find any FET configuration. The input impedance is in megaohms. So this 10 megaohms, 5 megaohms is more than what you require. So there is no need to increase it further. Already what is required as far as input impedance is concerned, what is required for you, it is available in the single stage itself. So where is the need for adding another stage or modifying it to have more input impedances? That requirement is there in BJTs, hence modified, and it result is in Darlington pair, but that requirement is not there. That necessity is not there in case of FET amplifiers. So Darlington is one important two-stage amplifier and cascode. Then what is this cascode? Already I told you, CE exhibits all good properties. That's why it is considered the most versatile. Out of the three configurations, most versatile configuration in case of BJT amplifiers is a CE, but it suffers one drawback. What is the drawback? Just now I mentioned. What is the serious drawback of CE? All good except that high frequency limitation is there. When I say high frequency limitation is there, you may not be able to appreciate this particular problem. But if I say we are communication engineers, all our operations. For example, modulation, demodulation, transmission, reception, all these things are done at low frequencies or high frequencies? High frequencies. Our frequency starts from kilohertz range. Kilohertz, 10 kilohertz, 20 kilohertz, kilohertz, megahertz, gigahertz. But CA has a limitation. It doesn't work as it is. It cannot perform at kilohertz. All its performance is at low frequencies. So high frequency limitation of C is a serious problem as far as we are concerned because we work with high frequencies. So then how to enhance its high frequency, this shortcoming? It's good, everything is good, only this problem. But that problem is a serious problem for communication engineers. So keeping this aspect, this overall picture in mind, they started working. What they want to do is they want to somehow remove this shortcoming, this handicap associated with CE amplifiers. So they come out with a design. In that design, they added another CB stage and they made some design changes or they proposed certain design changes, modifications, and ultimately they are able to give an amplifier which gives as good a performance as given by CA. CA single stage gives you, as I already told you, good performance. So this modified amplifier also gives as good performance as a single CA stage. Not only that, sometimes it even gives a better performance than single CA stage. And with that handicap, high frequency limitation issue is there now, that eliminated. Now, cascode, that combination is called cascode. Cascode means CE, CB. CE, CB together is cascode. This has a FET version also. In BJT, it is CECB. In a FET version, it becomes CSCG. As already told you, CS also it has this high frequency limitation, narrow bandwidth problem. If you go for cascode that configuration, then CS also gets rid of this issue. Now you can use it. Everything is fine, spotless, extremely good performance. Okay, so that is cascode. Next, differential pair. Differential pair is also two-stage amplifier. Here, two stages are CE, CE in BJT version. When it comes to FET version, CS, CS. One basic difference between Darlington, cascode, and a differential pair. Differential pair and other remaining two is that differential pair it accepts two inputs. Darlington accepts only one input. Cascode accepts only one input. Differential accepts, it takes two inputs. Their functioning is like this. It takes two inputs. First subtraction is performed. Subtraction. Inputs are subtracted from one another. The resultant is amplified. So first differencing, subtraction, and then it is amplification. So differencing and amplification is the functioning. These two terms define or describe the functioning of the differential pair. These are the importance of differential pair is it goes into the making of operational amplifiers. Operational amplifier, you all know, it is a widely used amplifier circuit. It is called operational. Operational means it is able to perform mathematical operations like addition, subtraction, mathematical operations, division, multiplication, integration, differentiation. Okay. So op amp is an analog amplifier. Keep it in mind. It is an analog amplifier. To design an analog amplifier, two, three stages are there inside. Two, three stages. For primary stage or fundamental stage or front end stage of op amp is it uses this particular differential amplifier. So that is its importance. Next, we go to tuned amplifiers. High frequency. They take high frequency signal, amplify it, and gives out amplified version. You can appreciate better the importance of tuned amplifiers if I say their application. You all know communications are two types. Electrical communications are two types. What are they? One is wire communication, another is wireless. Wireless is also called radio communication. Wireless and radio, these are synonyms. During the development process of wireless communication systems, in some countries they named it wireless. In some other countries, they started calling it a radio. When it comes to radio communications or wireless communications, in the design or in the functioning, you can find invariably two two ends. One is transmitter, another is receiver. Transmitter output is connected to an antenna, and receiver input is connected to another antenna. Two antennas. Radio communication means 99% of the times two antennas, transmitting antenna, receiving antenna. Now, tuned amplifiers. Tuned amplifiers are invariably used immediately after the receiving antenna. So, radio communication nowadays, all communications are except eating, drinking, everything uses wireless. Even for the keyboard connection to the system, we are using wireless. Am I right? Even mouse is connected to the system through. While everything is wireless, very few cases their communication systems are there which use wire. Most of the things are wireless. Radio. Radio means receiving antenna. Immediately after receiving antenna, you find tuned amplifiers. Why they are called tuned amplifier means amplifier, which amplifies the signal, which makes the signal large. That's okay. Why they are called tuned amplifier? Reason is the load, the load of this amplifier is a tuned circuit. Parallel LC, most of the times it is parallel LC circuit is the load. So the use is on the receiver side of radio communication. The name, the title tuned amplifier has come from the usage of a tuned circuit as the load in these amplifiers. Another important aspect of tuned amplifiers is invariably they are used. They use several stages. Most of the times it is four stage. Four up to four it's okay. Three stage, four stage tuned amplifiers. Okay. One more thing I want to tell regarding their functionality is tuned amplifiers not only amplify the signal but also they provide some kind of what is that filtering. They provide filtering. They provide amplification. Two things they do: filtering plus amplification. To provide filtering, to give that functionality to the amplifier circuit, tuned circuits are used as a load. That's also there. Next, power amplifiers we discuss later. Feedback amplifiers. What are feedback amplifiers? Feedback is a concept. This concept is widely used in engineering. When I say engineering, I mean mechanical engineering, I mean chemical engineering, I mean electrical, electronics. In every branch of engineering, you can find feedback. Go to electrical people, triple A. They must be studying. They are studying feedback. Hmm? Mechanical. There also you can find automobile engineering or what I can say. Everywhere it is there. Feedback. You have the importance of this feedback and understood from the fact that you have one subject. I don't know whether already it is taught to you or it may come later. It is automatic control system. So it is an important aspect feedback. As far as we are concerned, electronics engineering is concerned, feedback can be understood as a circuit technique. It's a technique. It is a technique by which one can improve the performance of device or circuit. Performance enhancement, that is the main function, main motto, main purpose of the feedback. There is a device, there is a circuit, I want to improve the performance. This is one way, employing feedback. One example I will give you. See, these transistors, FETs, these are made with semiconductors. Am I right? They are made with semiconductors. All semiconductor devices, they have one drawback, a serious drawback. That drawback is their performance, their properties, their characteristics are dependent upon temperature. Do you know this? You died also. You must have studied the characteristic change of a diode with temperature. Don't you remember? For every 10-degree rise in temperature, the reverse saturation current doubles and all that, that kind of thing. When reverse saturation current doubles, then what happens? Total current changes. Okay. So, point is, semiconductor devices, transistors, FETs, these are semiconductor devices and their characteristics, they vary with temperature. And we employ these transistors in the design of amplifiers. Okay, we employ these two transistors in the design, and in a day, if you take a day, in a day we have in the morning one temperature, midday another temperature, in the evening a different temperature. So temperature varies. In a day, temperature keep on varying. Not only that, seasons also we have in a year, several seasons. Season wise also temperature variation is there. Day variation is there, season-wise variation is there. So temperature is not a constant thing. Therefore, the performance or characteristic of amplifier circuit also, as it employs semiconductor devices, transistors, it also keep on varying. So do you like a cell phone which performs one way in the morning and another way in the evening? Do you want a cell phone which performs equally well throughout the day, or you want morning one performance, afternoon another performance? Which one you prefer? We want a constant performance from any device. Okay. So this issue is there. What is that? Gain variation. Gain variation with temperature, gain variation with aging. Several other issues are also there. So stability, lack of stability is an important aspect as far as these devices are concerned, semiconductor devices, and that gets reflected in the amplifier circuits also, which use transistors in their for their design. So stabilization, gain stabilization is an important aspect. Feedback is widely used in the stabilization of gain to arrest the performance deterioration due to temperature changes and aging process and all that. So we use negative feedback. Two types of feedbacks are there: positive feedback, negative feedback. We hardly use positive feedback. Most of the times we use negative feedback by proper sampling, by proper mixing, voltage series, voltage shunt, current series, current shunt. Different types of sampling, mixing methods are there. So by selecting appropriate one, we can stabilize. Gain stabilization is an important aspect. That stabilization. Apart from gain stabilization, feedback can also be used to reduce the noise. Noise reduction is possible. Several other aspects. It is possible to adjust impedance levels at input and output. For example, CB. You all know CB configuration, it's a voltage amplifier. It provides you voltage gain. Its current gain is nearly 1 less than 1. So CB is voltage amplifier. Voltage amplifier requires high input impedance and low output impedance. But if you might have studied CEP configuration in the last time, CB's input impedance is low. Its output impedance is high. It's a drawback. If see for voltage amplifier, input impedance requires to be high, but CB is voltage amplifier, its input impedance is low. So somehow you have to increase its input impedance to high level. Otherwise, what happens? Otherwise, gain keep on varying. Here one gain, there another gain, morning one gain, afternoon another gain. You don't want that kind of thing to happen. So input impedance requires sometimes to be increased, output impedance requires to be decreased, sometimes vice versa also. So impedance adjustments is one important aspect so that best performance is given by the amplifier. So for this adjustment also, this feedback is used. That particular aspect you are going to study. Oscillators. What are oscillators? Uh, See, you are studying these communications, analog communications. For example, amplitude modulation. What do you do in amplitude modulation? There is a signal, there is a carrier, single frequency. There is also a signal which carries information, also called baseband signal. We multiply carrier with the baseband signal. Am I right? So this multiplication results in carrier and two sidebands and all that. Carrier. How this FC is generated? Point of generating circuit is your oscillator. Already mentioned, oscillator is also an amplifier circuit. Oscillator is in fact a feedback amplifier. It's a feedback amplifier satisfying certain condition. That condition you are going to learn or study about it later. Unity loop gain. a feedback amplifier which satisfies this unity loop gain condition. It starts working as a oscillator. So it's an amplifier. All are amplifiers. Lastly, we have to discuss about power amplifiers. Power amplifiers enhances the power of the signal. Voltage amplifier enhances the voltage in the signal. Current amplifier enhances the current, whereas power amplifier enhances the power. There are one or two distinct features as far as the power amplifiers are concerned. They are amplifiers only, amplifier circuits. Basically, amplifier circuits. One or two features, distinct features. What are they? The transistors we use for providing amplification, power amplification in power amplifier circuits, those transistors are somewhat, they are made differently. Differently in the sense they must be capable of dissipating more and more powers. If you go to the specification of any transistor, a data sheet is available with a transistor. In that data sheet, a lot of information is provided. One of the piece of information that is provided in the data sheet pertaining to amplifier transistor is that the maximum amount of power the transistor is capable of handling. If you try to give or if you try to inject more power into that transistor, then it simply it gets destroyed. Okay, so there is a limitation, power limitation, dissipation limitation. These transistors that are used in power amplifiers, they are made in such a way that they are capable of handling more and more powers. This is one aspect. Another aspect is in the design of power amplifiers as well as in the analysis of power amplifiers. The techniques which we use, normally we use with other amplifier circuits, those techniques they are not valid. Example, suppose I want to analyze a Darlington pair. Then normally what do? We take up the amplifier circuit and then we extract AC equivalent circuit. In that AC equivalent circuit, we replace the transistor with one or other linear equivalent circuit, H parameter circuit or T circuit, pi circuit. Several types of equivalent circuits are there. We replace the transistor with the circuit and then we do circuit theory. We use circuit theory principles like Ohm's law, Kirchhoff's law, this law, that law, and we analyze it. In the design also we use similar laws, same laws in the design. But that type of analysis is not valid in case of power amplifiers. The reason is most of the amplifiers, this point you must be, it must be there in your mind. Transistors are basically nonlinear circuit, nonlinear devices. All transistors, whether you use BJTs or you use FETs in the design of circuits, they are devices, transistors themselves nonlinear. So therefore, the circuits in which these nonlinear devices are embedded, the circuits themselves are nonlinear. Under the laws which is studied during circuit theory, Ohm's, for example, Ohm's law. Ohm's law, if you recollect the statement of Ohm's law, in the beginning itself, it says that in a linear element, voltage is, for example, in a linear resistor, voltage across the resistor is proportional to current. Or if you consider Thevenin theorem, Norton theorem, Telegraph theorem, any theorem, all those theorems which you studied, laws which you studied in circuit theory, they are valid for linear circuits. But as it is, amplifiers are non-linear because transistor is there, diode is there inside the circuit. So those laws are not useful for you. As it is, they are not useful for the analysis of amplifier circuits. then what to do? What is the way out? A way out is we replace the transistor with an equivalent circuit. This equivalent circuit is a linear circuit. It is an approximate circuit, but it is a linear circuit. Once you replace transistor with a linear circuit, equivalent circuit, then the entire circuit becomes a linear one, and hence we can use all those laws. But when it comes to power amplifiers, that type of thing you cannot do. Reason is equivalent circuits are valid only when signal in the amplifier, the voltage of the signal, maximum voltage of the signal in amplifier is very less than Vt by 10. Vt means volt equivalent of temperature 26 millivolts. 26 millivolts by 10 means 2.6 millivolts. And signal must be less than, very less than 2.6 అంటే ఎంత ఉండాలి? Maybe 1 millivolt, half millivolt or something like that. But that type of situation doesn't exist in case of power amplifiers. Their voltage levels are maybe hundreds of millivolts or tens of volts. So that equivalent circuit business, linear equivalent circuit business, that thing you cannot use in case of power amplifiers. They have different type of analysis techniques, different types of things, design techniques. So regarding power amplifiers, what you have to keep in mind is two distinct features of these power amplifier circuits are: one, the transistors which we use in the design is power transistors. They are called power transistors. They are capable of dissipating lot of heat. This is one aspect. They are not ordinary transistors. They are not transistors that are used in other types of amplifier circuits. This is one aspect. Second aspect is their design, their analysis is somewhat different from the design, the analysis of other amplifier circuits, because mostly they work in the nonlinear region. Several different types are there. Most prominent among them are A, B, AB, C. These are prominent types. Other types are also there. D is there, E is there, F is there, H is there, J is there, K is there. So many types are there. All those things they are introduced. Basically, one or two points regarding A, B, and C. A means it gives a clear amplification. Sorry, clear or clarity. Clarity is important. A gives highly clear amplification, no distortion, little distortion or no distortion. If you want, for example, audio amplifiers are expected to give clarity, clarity of voice. Am I right? Hmm? You don't mind to be even less efficient also. What we want is clarity. If you want clarity, then A. C gives best efficiency, maximum efficiency. So it is clarity, efficiency. A means more clarity, less distortion, less efficiency. And as you move from A to B, A, B, C, clarity comes down, efficiency goes up. Okay. And other types are also there. All those things are discussed at length in your regular classes.